Okay, so this is 4.1c. We're still on reflections of graphs, and I just want to try to clear a couple things up as I have been looking at the bottom of page 251 in the green. So it says that we can make this graph here by reflecting the graph y equals f of x across the x-axis. So what we're going to do, we're going to graph that. Okay, we have no idea what it looks like, but let's just say it's y equals 2x plus 3. Okay, let's just make it 2x squared plus 3. Make it a parabola. All right, what that's saying is if you want that to reflect across the x-axis, then put a parenthesis around it and put a minus sign in front of it. Okay, then it's going to reflect across the x-axis. Okay? And if you want it to reflect across the y-axis, it says y equals f of negative x. That can be reflected across the y-axis if we take our original and our x value we change to its opposite. Okay? So hopefully that helps a little bit as you're looking at these. And we'll get into more of this again shortly. But let's continue on here. So examples 7 and 8 I'd like for you to look at on your own. There's really nothing real scary or real difficult with that. I guess the little bit of a struggle here is they're not doing a whole lot with the stretching, compression, reflecting, and all the shifting and stuff. A little bit more on 7, example 7. But use your graphing calculator, plug some numbers in there, and see what you get there. But I want to jump up to symmetry, even in odd functions. Okay? So you've got symmetry with respect to the y-axis, which means it's going to be symmetrical. Like if I have a parabola here, the distance from there to there is going to be the same as the distance from there to there, making it symmetrical. You're also going to have it symmetrical in respect to the origin, and then you're going to have it symmetrical in respect to the x-axis. So that's what we're going to look at here. Okay, so how in the world do you find out if a graph is symmetrical with respect to, let's say, the y-axis? Okay, so we've got our graph here, and we want to find out if it's symmetrical with respect to the y-axis. Well, all we have to do is take our function and take our f of x, and instead of using an x there, we're going to use a negative x. Okay? So if that gives me the same value as an answer, then it is symmetrical with respect to the y-axis. And so what they say is if we have f of x, and that's equal to f of negative x, then it's symmetrical with respect to the y-axis. Okay? Which basically means that if we have a point xy and we have another point negative xy, and they're both on the graph, well, then it's symmetrical, because what we did is we went over a positive value and up, or a negative x and up. Okay, so notice our y here was positive, and our x here was positive here, but negative here. But we still ended up at a point on the graph. So therefore, it is symmetrical. And they say that when it is symmetrical with respect to the y-axis, it's called an even function. If you want to find out why it's called an even function, you can look there, middle of page 254. It has to do with the exponents. If the exponents are even, then they're symmetrical around the x-axis. But there's more the more even functions that are just that have exponents other than even, but that's where they got that. So anyway, if you care. All right, so let's continue looking here. If you're looking at something in respect to the origin, if you want to find out if your graph is symmetrical with respect to the origin, then the function of x is opposite has to be equal to the function of x, and then you change it to its opposite once you're done. Okay? So here you're doing the function of x, but you're doing it with a negative x, and here you're doing it with negative f of x. You're finding f of x and then making it negative. And when you do that, if it is symmetrical in respect to the origin, it's called an odd function. Okay, so let's see if they give us a chance here to try an example. They do in example 9. So we're going to get to that in just a minute. So just hold on to that for a minute and let's do one last one, and that is being symmetrical with respect to the x-axis. Now, one of the things that you'll notice is if we have something that's symmetrical with the x-axis, problem is it's not a function because it doesn't pass the vertical line test. Okay? But anyway, you'll still run into graphs that are symmetrical with respect to the x-axis. So, for every point xy, there will be a point x negative y, and that will be on the graph. Okay? So, if we come over x up, that's a positive x, and then we went up, so we went positive y. To get here, we went over positive x, but we went down, so we went negative y. So that's what happens with respect to the x-axis, is the x values are the same, the y values have the same number, but they're opposite in sign. All right, so let's look at symmetry in example number 9, and hopefully we'll clear up any of your struggles with my explanation here. So, the first one, A, gives me this problem. It's always so much easier when you're actually using examples instead of labels and stuff. All right, so first of all, we're going to find out if this is symmetrical with respect to the x-axis. And then we're going to look at it with respect to the y-axis and then the origin. So what this means is, are these two equal? Are they equivalent? Well, if I have y equals 2x squared over x squared plus 1, that would be this. This one would look like this. My y is negative. Are these two equations the same? No, because this one doesn't have a negative and this one does. So therefore, it is not symmetrical with respect to the x-axis. All right, so let's see if it's symmetrical with respect to the y-axis. So with respect to the y-axis, our original function, which is this one here, has to equal this function here with the x negative. So this is what it'll look like. Okay, this one here looks like 2x squared over x squared plus 1. Okay, that's what this one is. It must be equal to that. Okay, and what that means is we're going to, every time we see an x, we're going to make it negative. So there's 2, there's an x, so I'm going to make it negative, over, there's an x, I'm going to make it negative, plus 1. Now, the question is, are these two equal? If they are, then they are symmetrical around the y-axis. So let's give this a shot. So let's do some work right here. Negative x times negative x is positive x squared. Negative x times negative x is positive x squared. That is the same as that. So therefore, it's symmetric with the y-axis. And it is an even function of x because it is symmetrical with the y-axis. So let's see if it's symmetrical with the, let's get rid of some of this junk here. Let's see if it's symmetrical with the origin. Alright, so to be symmetrical with the origin, we have our x, and we have negative x, and we have y, and we have negative y. So what we're going to do is we're going to replace x with negative x and y with negative y. Okay, so this is what it's going to look like. Let me turn this off for a minute. I probably should not turn it off, but let's take the original equation, which is up here, and it's right here. So let's take the original one, 2x over x squared plus 1 equals y. I want to know if that's going to equal, again, we're putting a negative y and a negative x. Wherever we see a y, we're putting a negative y. And wherever we see an x, we're putting a negative x. And we want to know if those two are equal. Okay, so when you do this, you're going to find out, again, like we did before. Well, let's get rid of some of this junk. Okay, so we're going to leave the one on the left alone because that's the original one. We're comparing that. So we get negative y equals 2x squared over x squared plus 1. Is that equal to that? No, because this one does not have a negative. So therefore, it is not symmetric with respect to the origin. All right? All right, so I am over 12 minutes here, so I am going to make a fourth video. It'll be a shorter one, but I just don't want to keep going on and on with this one. So let's go to a fourth one, 4.1D.